Thank you very much for introduction. My name is Marcin Gronowski. I'm member of Quantum Molecular System Group, led by Professor Michał Tomza. As you expected, I will talk about the few atom complexes which are formed in the ultracold collision. So we are going to discuss during this presentation about really like atoms, or small systems, and I will discuss mostly about the results which came from the theory, but I would like to underline at the beginning that the results which I'm going to present are part of many different collaborations, including the collaboration with experimental groups from MIT and Harvard. And I would like to also underline that huge contribution from Timur and Tias in the field of the scattering calculations. Okay, so as you heard, especially during the first day of this conference, there are a lot of new experiments with ultracold molecules. Generally, what we know how to create them in a very efficient way, at least some of them. There are plenty of ideas what we can do with them, how to probe the chemistry, how to study the physics, and finally we can have even like a Bose-Einstein condensate of dipolar molecules. So in all of these experiments, the problem which appear, or that subject which could be problem for at least some of them, is something what we call as a ultracold sticky collision, which is in another form, which is in fact the formation of collisional complex from ultracold molecules. And this collisional complex is the main subject of this talk. So we discuss ultracold molecules, so it's worth to mention that we usually deal with very low collision energies. In the Kelvin scale, it is like a small fraction of the Kelvin, 10 to minus 6, 7, 8. So when we compare this to the typical range of the energies in the molecules, we see that there's more or less the separation between different hyperfine levels. And then we have the sticky collision. There are still plenty questions related to them, starting from the lifetime, about the dynamics of these complexes, reactivity, maybe about the conservation of different quantum numbers during this collision, and so on and so forth. We have also a little bit more general question about breakdown of von-Oppenheimer approximation, or maybe about how we should think about sort of a transition from quantum to classical regimes. So I'm not going to answer on all of these questions, but I would like to start from the beginning. So generally, when we talk about hyperfine, it means that, and couplings, it means that we have several different sources of angular momentum. And just comparison, in case of atom, we have only electronic spin and nuclear spin, and only one coupling between them. When we go to the rigid molecule, we have also rotation, at least in case of diatomic molecules. And generally, this part is well known and pretty well studied, both by high resolution spectroscopy and by the different resonances. But in the case of the collisional complex, we have a lot of couplings, very little is known, and especially we have also rotation of each of the components in the complex. And the question is, if the interaction may change, may introduce some new couplings. And I would like to start from the collision or complex form from the collision of two closed shell molecules. Something what can be measured in the experiment is the lifetime of this complex. And from the theoretical side, the lifetime of this complex is related to the density of states. And when some people computed the density of states and from them the lifetime is predicted is usually orders of magnitude shorter than the experimental one, which means that something is wrong with the density of states. Just to give you a little bit intuition what means the collisional complex, this is the global minima of the complex formed from the collision of sodium-potassium molecule. Yes, so you see this perfectly symmetric. These colors represent the electronic density, which is also symmetric, and we have four, let's say, more or less the same bounds there. So it means that something what was missed in the previous study, it was like any hyperfine interaction. So the previous study assumed that the hyperfine interaction is exactly the same as in the case of the diatomic molecules. And what we did, we calculated the hyperfine interactions in the function of the intermonomer separation for different orientation of a sodium-potassium molecule. And generally for the long range part, as you see here, for example, and other couplings also, this is more or less as the constant value. But when we look on the short range part, this coupling became quite strong. But when you look on the strength of this interaction is 600 reciprocal centimeters, so this potential is not very, very deep. So when we repeat more or less the same for sodium rubidium, we see also a lot of changes at the short range part and also new type of couplings which are due to the interaction, for example, between nuclear spins from different molecules. So generally what we can say, we should include more states in the calculation of the density of states, and probably this is something what we would like to do in future. Generally, probably this theoretical lifetime will be closer to the experimental one. So this is the moment to go to another experiment, which is a collision between KRB molecule and RB. And generally, it is a beautiful experiment in which can start from the rubidium in the ground state or rubidium in the excited hyperfine state. And generally, what is experimental conclusion from the study, that the lifetime of the complex is very sensitive to the initial hyperfine state. Just to give you a scale, in the case of the rubidium, the lowest hyperfine state, the lifetime is on the order of milliseconds. In the case of the excited hyperfine state, it is orders of magnitude shorter. Additionally, what they did, they measured the ratio between different rotational states after the collision. This is more or less the experimental results. And if we assume that the mechanical rotation is conserved, the ratio should be 1 to 1 to 1, which is completely different from the experimental. But if we assume that all degrees of freedom are scrambled, then we got more or less agreement with the theory, between theory and experiment, which is suggestion that we need some kind of a coupling between rotation and spin, either electronic or nuclear spin. And usually the main interaction which involves the nuclear and electronic spin is something what is like a classical hyperfine, so the coupling between just nuclear spin and electronic spin. But as you see here in this equation, there is no any rotation, there is only the spin and nuclear spin. So we do not expect that it can couple to the rotation. The main contribution is the coupling between electronic spin and rotation. And what you see here on this plot, this kind of a peak-shaped structure. So this is the spin rotation coupling, the function of the intermonomer distance, and this peak nicely coincides, is more or less in the same position as the conical intersection between the ground and the excited electronic state. And when we do a lot of cuts through the potential energy surface, we see that the position of the conical intersection is pretty sensitive to the tiny change in the geometric parameters, and with this change, the position of this peak also can move a lot. And so this is a good moment to mention about the shape of the potential energy surface. It depends in which coordinates we plot. If we plot like here in the function of the distance between rubidium atoms and potassium, we see generally two minima, but there is a little bit which seems on this plot like a barrier. This is in fact the conical intersection. And generally what we see, if there is the collision between here, there is no really barrier for the exchange reaction. If we look on the second plot, which is in the Jacobi coordinates, we assume here that the molecule, KRB molecule is rigid rotor, then we see a lot of anisotropy here. What I would like also to mention that this nice coincidence that the conical intersection is exactly in the same position like the minima on the excited state potential energy surface. So we try to probe a little bit the configurational space to know if we really need to include everything in the collision, in the collisional calculations. And for this we do classical molecular dynamics, and generally what we see here, we observe the fraction of the trajectories which can be classified as reactive or non-reactive, and generally it depends on the initial orientation, which is not very surprising, but more or less on average half of the trajectories are reactive, so it means that we have to include probably all degrees of freedom. We also calculated the density of states exactly for our system, assuming that the mechanical rotation is conserved, and the lifetime is once again orders of magnitude shorter than the experimental one, which is not very surprising. And this strong suggestion that that something is not conserved, I mean, and we need some kind of a coupling. I should mention about the other theoretical work, which works on more or less the same complex, and when they assume that the J or that rotation is not conserved, this density of state could be orders of magnitude shorter. Because I'm running out of time, I would like also mention once again that in the case of the third example, when we have the collision between sodium, lithium molecule and sodium, we have huge anisotropy of potential. And then in the scattering calculation, we need to include this anisotropy. Otherwise, our results are scattering results can be quite orders of magnitude wrong or far from the exact solution. So just a take-home message. In the case of collision between at least ultra-cold molecules, even if the interaction is weak, this complex cannot be treated as a simple sum of the two independent molecules. And this is time to say thank you for all colleagues from Michał's Tomza group for very nice discussion and also for funding. Thank you very much.
Thank you, Marcin. Is there any questions? Yes.
Yeah, thanks for the very nice talk and the nice results. So you showed this conical intersection for the potassium rubidium was quite deep in the potential energy surface.
Yeah.
And I was kind of curious because for me this would mean that I would expect very chaotic dynamics also like in the spin degree of freedom. So in this regard, I'm kind of surprised that you see such large differences between the different hyperfine states, because I would kind of expect everything to be then kind of chaotic. Can you give some interpretation?
So if I understand correctly, you conclude that there should be no this difference in the lifetime, yes?
Right.
Yeah, this is something what it's not clear for me also right now. Because yes, we have the conical intersection, which is pretty deep, yes. So here, even if we assume the tiny change, because this dash line is the excited state, potential energy curve, the solid line is the ground state, and the difference between each of the curve is only like between classical turning points for the ground vibrational state. So this is like a tiny difference, and we can bring this conical intersection shift by a little bit, but when we change it more, yes, in fact, everything here or on this diagonal, it's like a conical intersection. But sorry, right now we do not have. What is also surprising when we include everything in the scattering calculation, when we assume rigid rotor approximation, there is no really sensitivity to this. So it is probably the situation that we have to couple the anisotropy of the potential, this reactive channel, with the couplings, which is not trivial right now for the theory. So this is what is the state of the art for the scattering theory right now.
Thank you. Any more questions? No? Okay, then let's thank again our speaker.
Thank you.